So I want you to picture this. You've got a high-altitude drone,
Yeah.
right? And it's loitering at, say, 20,000 feet.
Right, which is not a friendly environment.
No, not at all. The ambient temperature is hovering around negative 30 degrees Celsius. You've got these just vicious crosswinds. And on top of all that, it's operating in heavily contested airspace. So there's electromagnetic jamming everywhere.
It's basically a nightmare scenario for any piece of electronics.
Exactly. But, when the general public pictures a machine like that, the focus immediately goes to the tactical stuff, the payloads.
Yeah, the cameras.
Right, the synthetic aperture radar, or the multispectral targeting gimbals, the stealth wings. We completely romanticize the aerodynamics and the optics. But the reality is the entire platform is merely a highly engineered glider, just waiting to fall out of the sky if it doesn't have this invisible, hyper-paranoid electronic brain humming away deep inside the fuselage.
Yeah, the aerodynamics might get the aircraft off the ground, sure, but the engine management system is what prevents it from becoming, a kinetic projectile over a populated area.
Right.
The brain of the aircraft is the ultimate single point of failure, which is why it's subjected to a level of engineering scrutiny that, frankly, most consumer electronics designers would find completely incomprehensible.
And that's exactly what we are stripping down to the circuit boards today. We're doing a massive, comprehensive deep dive into a source document that dictates exactly how these systems are built.
It's a fascinating document.
It really is. Specifically, we're unpacking a master architecture guide. It's this dense, multi-tiered requirements matrix, globally recognized in aerospace manufacturing, and it's originally codified in our source material as the S, or UAV, which is Engine Management System.
Yeah, the customer requirement document.
Right. And I look at this thing, and it's less of a standard form and more of a literal survival guide for a flying robot. Okay, let's unpack this. Our mission today is to decode this absolute maze of military specifications, thermodynamics, and software safety standards to show you how unforgiving the physics of modern aviation actually are.
I like that. Survival Guide captures the essence perfectly because, a requirements matrix of this caliber, it isn't drafted in a vacuum.
Right. It doesn't just come out of nowhere.
Exactly. Every single mandate, every temperature threshold, every single vibration tolerance in this document, it's written in the wreckage of past aviation failures.
Oh, wow. That's a dark but true way to look at it.
It's the reality of the industry. When you read a requirement dictating that a specific memory controller must withstand a 40G shock, it's because at some point in aerospace history, an aircraft hit the deck hard, a commercial-grade silicon chip sheared off its mounting pads, and the engine flamed out.
So they write a rule so it never happens again.
Precisely. This matrix represents decades of codified, uncompromising engineering paranoia.
So let's look at how that paranoia is structured on the front end, like long before a single line of code is compiled. Because the aerospace industry operates on a project management pipeline that looks absolutely nothing like what we see in tech today.
Oh, it's the exact opposite of Silicon Valley.
Right. Tech loves the move fast and break things ethos. Agile development, push a minimum viable product, and then just patch it via Wi-Fi later. Aerospace outright rejects that.
They have to. In commercial software, a catastrophic bug means what? A user gets a 404 error?
Yeah, your app crashes.
Right, and you just push a hot fix over the weekend. But in an unmanned aerial vehicle, a catastrophic bug means a quarter ton of metal and jet fuel impacts the ground at terminal velocity.
Which is unacceptable.
Completely. So the airspace design pipeline forces this cost-to-fix curve that becomes exponentially more punitive the further you advance in the project.
Okay, so the document lays out this brutal gauntlet of development nodes, right? You've got conceptual design, then the system requirement review, the SRR, then the preliminary design review, critical design review, all the way through hardware in the loop simulation before you even approach a start of production.
Yeah, and at each stage, the cost of making a mistake skyrockets. Discovering a logic flaw during that initial SRR, the system requirement review, it might cost, a few hours of an engineering team's time to update a flowchart.
Basically just erasing a whiteboard.
Right. But discovering that exact same flaw later, during hardware in the loop testing, that means scrapping physical prototypes. Custom circuit boards go in the trash.
Ouch.
And if you uncover it during a flight test, that can cost millions of dollars or trigger a complete programmatic reset by the regulatory authorities.
So that critical design review, the CDR, is basically the point of no return.
It acts as a hard stop. You do not even touch a soldering iron until the mathematical models prove the architecture is flawless.
Wow. Okay, so moving past the timeline, the document categorizes the hardware moving through this pipeline by weight class. And the physical reality shifts pretty dramatically between them. We're looking at small UAVs, which they define here as 25 to 150 kilograms.
Right.
Medium is 150 to 600 kilograms. And large encompasses the MAIL and HAIL platforms.
Medium and high-altitude long endurance.
Yeah, so anything over 1,600 kilograms. Now, obviously, a 25-kilogram drone and a 2-ton drone have wildly different propulsion needs. But what struck me is that they're bound by the same international airspace passports, so to speak.
Yeah, the target markets listed are NATO, the U.S. Department of Defense, and the European Union Aviation Safety Agency, or ESA.
Right, and to operate in those spaces, the system must comply with all these acronyms. STANAG 4671 and 4703, ESA CS23, and MIL-HDBK 516.
So those STANAG standardization agreements, they're critical to understand if you want to grasp how joint military operations function.
Okay, break that down for us.
Well, STANAG 4671 creates a unified airworthiness framework for UAVs operating in NATO airspace. So imagine an Italian ground control station needs to suddenly assume command of a UK-manufactured surveillance drone mid-flight.
Okay, handoff between countries.
Exactly. The underlying engine management telemetry, the fail-safes, the data architecture, it all must speak a compatible, mathematically verifiable language of reliability. Otherwise, that handoff is too dangerous.
Right, and the ESA CS23 does a similar thing for civilian airspace.
Okay, yeah, it adapts the safety standards of light utility aircraft to unmanned systems. That way, these drones can share congested airspace with commercial airliners without introducing unpredictable risk variables.
Speaking of unpredictable risk, that brings us to a mandate in the document that I think requires some serious scrutiny. The text demands strict adherence to design assurance levels, specifically DO-254 for complex electronic hardware and DO-178C for software.
The gold standards of aviation safety.
Right. And it states that the architecture must support requirements up to DALA, which translates to extremely critical.
Yeah.
Now, let's play devil's advocate here for a second.
Okay, go ahead.
I understand slapping a DLA requirement on a Boeing 7777, hundreds of people on board. But why does a 25-kilogram drone, a relatively small machine with 0 human occupants, require the exact same extremely critical DO-178C software traceability as a massive passenger airliner? Because to me, that seems like a massive misallocation of engineering resources for an unmanned platform.
I get why you'd say that. It seems disproportionate, right? Until you factor in kinetic energy and the density of modern airspace.
Okay, how so?
So, design assurance level A is mandated when a failure condition is classified as catastrophic, meaning it prevents continued safe flight and landing. Now, sure, a 25-kilogram drone flying over an unpopulated desert doesn't pose a massive risk.
Right, it just hits the sand.
But the mission profiles for these platforms increasingly require them to loiter over densely populated urban centers, or they have to transit through Class B commercial airspace just to get to their mission zone.
Oh, I see.
A 25-kilogram drone falling from 10,000 feet. That is a lethal projectile. The air traffic control infrastructure simply cannot tolerate a machine that might spontaneously reboot its engine controller while crossing the flight path of a commercial departure out of JFK.
Yeah, gravity is entirely indifferent to whether the aircraft has a pilot in the cockpit.
Precisely. That's the underlying logic of DO-178C. And the really defining characteristic of this standard is that you cannot retrofit it.
What do you mean?
You can't just build a functional engine management system using standard, commercial coding practices, prove that it runs well on a test stand, and then attempt to apply DO-178C certification after the fact. It doesn't work like that.
Because the standard isn't just about the final executable file, right? It's like a forensic audit of the entire software lifecycle.
Exactly. It requires a bidirectional traceability matrix.
Okay, what does that look like in practice?
Well, you start with a high-level requirement. For example, if engine RPM exceeds 10,000, cut fuel injection to prevent catastrophic mechanical failure.
Makes sense.
That requirement must then trace down to a specific software architecture design, which traces down to specific lines of C code, which traces down to a specific unit test designed solely to validate that one condition.
Everything is linked.
Yes. Furthermore, the standard requires modified condition decision coverage, or MCDC, for DALA.
MCDC. Sounds like a rock band, but I'm guessing it's a lot less fun.
Definitely less fun. It means the testing must prove not only that every line of code executes, but that every possible Boolean condition independently affects the outcome of the decision.
Wow.
And if an auditor finds dead code lines of programming that have no traceable requirement, or maybe some undocumented features a developer added just for convenience,
What happens?
the certification fails. The entire software block often has to be discarded and rewritten from scratch.
Wow, so it is the ultimate defense against spaghetti code. You're proving the intent of the software just as much as the actual function.
Exactly.
But, while the software engineers are mapping out all this Boolean logic, the mechanical engineers are fighting an equally unforgiving battle against thermodynamics.
Oh, the physical forces are just staggering.
Yeah, the mission profile demands operation in ambient temperatures from -30 to +55 Celsius. Launch modes include catapult and rocket-assisted takeoff, or RATO, and recovery includes parachute drops and arresting gear.
I don't think people realize the violence of an arresting gear recovery. It cannot be overstated.
Really, just hitting the wire.
Oh, yeah. The aircraft transitions from flight speed to absolute zero in a matter of seconds.
Wow.
That induces massive deceleration forces across every single mounting bracket, sensor harness, and fluid line.
Basically a controlled crash.
Exactly. And then you have rocket-assisted takeoffs, which subject the internal components to instantaneous crushing G-forces in the exact opposite direction. The engine block, the fuel delivery mechanisms, all those delicate electronic sensors, they have to absorb these kinetic shocks in blistering desert heat or freezing Arctic conditions without a single disruption to the combustion cycle.
Unbelievable. Let's break down the mechanical heart of this system then, because the engine specifications are super fascinating. The document outlines support for 2-stroke and 4-stroke piston engines, which, are standard fare, but it specifically mandates support for Wankel rotary engines.
Yeah, the rotary.
With displacements mapping from 44 cubic centimeters up to over 1,300. Now, the Wankel is a brilliant but notoriously temperamental piece of engineering.
Very true.
Instead of pistons moving linearly up and down, you have this triangular rotor sweeping inside an epitrochoidal housing. And the massive advantage for a UAV, as I understand it, is that a rotary engine has no reciprocating mass, violently changing direction thousands of times a minute.
Right. The reduction in vibration is the primary driver for Wankel adoption in this aerospace sector.
Because of the cameras.
Exactly. When a drone is carrying a highly sensitive, multi-million-dollar optical targeting gimbal, the high-frequency vibration from a typical 2-stroke piston engine can induce micro-jitters in the imagery. It severely degrades the synthetic aperture radar or the long-range optics. The Wankel, by comparison, spins incredibly smoothly.
That's not perfect.
Far from it. The geometric design of a rotary engine creates a long, flat combustion chamber with a highly uneven thermal profile. The intake side is constantly cooled by incoming air, while the exhaust side is just constantly superheated.
Right.
And sealing that combustion pressure relies on apex seals at the very tips of the spinning rotor. Those seals have historically been the Achilles heel of the Wankel design.
And the challenge of keeping those apex seals happy is compounded exponentially by the fuel mandate in this document, because this is where the physics become incredibly hostile.
Oh, the heavy fuel mandate, yeah.
The EMS must be capable of running these engines on heavy logistics fuels.
Yeah.
We're talking JP8, Jet A1, JP5. The military operates strictly on a single fuel policy, right? To eliminate the logistical nightmare of transporting highly volatile aviation gasoline for drones, diesel for ground vehicles, and jet fuel for helicopters.
Right. They want one unified liquid powering the entire theater of operations. It just makes supply chains infinitely easier.
Makes total sense. But asking a small displacement Wankel to burn JP8 sounds like a thermodynamic nightmare. I mean, JP8 is essentially a highly refined kerosene. It has a high flash point. It does not vaporize at room temperature like regular gasoline does.
No, it really doesn't. Trying to start a cold-soaked Wankel engine on JP8 at -30°C, that requires absolute brute force engineering.
How so?
Well, the fuel exhibits high viscosity at those temperatures. It behaves more like a thin syrup than a combustible liquid. So when it's injected into the cold combustion chamber, it refuses to atomize. It just clings to the walls of the rotor housing.
So trying to ignite JP8 heavy fuel in a freezing drone engine sounds like trying to light a wet log on fire with a single match.
That is a perfect analogy. The match won't do it. To achieve ignition, the engine management system has to utilize a capacitor discharge ignition, or CDI, system capable of generating 25 kilovolts of electrical potential.
25 kilovolts, that is not a standard automotive spark.
Not at all. 25 kilovolts creates a plasma channel intense enough to forcibly break down the heavy hydrocarbon chains of the JP8. And on top of that, the document mandates dual spark plugs per rotor to guarantee ignition and ensure a complete flame front across that elongated rotary combustion chamber.
2 massive sparks just to get the wet log burning.
Exactly. But the hardware is only half the solution. The software has to handle the rest via cold start mapping.
Okay, how does the software help start the engine?
The FADC, the Full Authority Digital Engine Control, reads the ambient and engine block temperatures. If it sees -30, it accesses a specific lookup table. It commands the fuel injectors to pulse with a completely different duration and timing phase.
So it changes how much fuel is going in.
Right, aggressively overriding the standard stoichiometric ratios. It basically floods the chamber with enough heavy fuel to guarantee a localized combustible mixture somewhere near that spark plasma. It might also engage physical intake preheaters to artificially raise the temperature of the incoming air mass before it ever reaches the combustion chamber.
Just fighting the cold every step of the way. But you know what's really interesting is that the thermodynamic challenges don't actually stop once the engine is warm.
Oh, they just change form.
Right. As the drone climbs to 20,000 feet, it runs into atmospheric pressure issues, specifically vapor lock. We know that as altitude increases, atmospheric pressure drops, which lowers the boiling point of liquids.
Right, basic physics.
At 20,000 feet, the ambient pressure is less than half of what it is at sea level. So the ambient heat from the engine block transfers into the fuel lines. Without intervention, that heavy JP8 will literally boil inside the fuel lines before it ever reaches the injectors.
And that is a huge problem. Standard fuel pumps, particularly the lightweight brushless DC pumps they use in aviation, they are designed to move incompressible fluids.
So liquids.
Yes. If the fuel flashes into vapor within the line, the pump cavitates. It just spins in gas, the fuel flow ceases instantly, the injectors fire empty gas, and the engine starves.
Okay, so if you've ever driven up a mountain and felt your car get sluggish, imagine what a drone experiences at 20,000 feet. And how this checklist anticipates that exact physics problem. How do they engineer around it?
The architecture dictates a continuous flow, pressurized fuel return system.
Okay, explain that.
Normally, fuel might just sit in a dead-end line waiting to be injected. But here, the pumps continuously flow an excessive volume of fuel from the tank, past the hot engine block, and then immediately route the unused portion back to the main fuel cell.
So it's always moving.
Mm-hmm.
And the dynamic pressure regulator at the end of that rail is doing the heavy lifting there, right? By restricting the flow of the returning fuel, it artificially inflates the pressure inside the entire fuel line loop.
Exactly. And that elevated pressure raises the boiling point of the JP8 far above the engine's ambient heat transfer limits, maintaining it in a liquid state.
Oh, wow.
Furthermore, that continuous flow constantly flushes the heated fuel back into the massive thermal sink of the main fuel tank, so it prevents any localized heat soaking near the injectors.
That is such an elegant solution to a really complex physics problem.
What's fascinating here is that the drop in atmospheric pressure creates a parallel crisis for the air intake as well. I mean, an internal combustion engine is essentially just a giant air pump. At high altitudes, the air density plummets. There are far fewer oxygen molecules available per cubic meter. So a naturally aspirated engine will suffer a catastrophic loss of volumetric efficiency and horsepower.
Just can't breathe.
Right. So the architecture mandates altitude compensation via exhaust-driven turbochargers. But bolting a turbocharger to an engine operating across a 20,000-foot altitude delta requires incredibly precise electronic management.
Yeah, you cannot rely on a traditional mechanical spring to control the turbocharger's wastegate under those conditions.
No, absolutely not.
Because a mechanical spring acts purely on differential pressure. As the drone climbs, the ambient pressure outside the spring drops, which fundamentally alters the spring's effective resistance. The turbocharger would just overspeed in the thin air, pushing the compressor map past its surge line and potentially destroying the turbine blades.
This is exactly why the document specifies an electronic wastegate managed directly by the FATC. The engine controller continuously reads the barometric absolute pressure, so the outside atmosphere, and the manifold absolute pressure, the dense air being forced into the engine.
Okay.
The software calculates the exact compressor RPM required to maintain the target manifold pressure regardless of altitude. And then it drives a high-speed electric actuator to micro-adjust the waste heat valve.
So it's constantly tweaking it.
Hundreds of times a second. It bleeds off exactly the right amount of exhaust gas, keeping the turbocharger precisely within its optimal efficiency island on the compressor map, whether the aircraft is taking off at sea level or loitering over a mountain range.
Yeah, it's just nonstop calculation. And, reading the exhaust gases to maintain that perfect combustion ratio brings up another really fascinating chemical challenge mentioned in the requirements.
Yeah.
The system utilizes wideband oxygen sensors in the exhaust stream to provide closed-loop feedback on the air-to-fuel mixture. But JP8 is a dirty fuel. It contains elevated levels of sulfur and complex additives designed for lubrication and anti-icing.
Yeah, it's not clean, like premium unleaded. When JP8 burns, those sulfur compounds vaporize. Now, a standard automotive wideband oxygen sensor relies on a porous ceramic element, typically zirconium dioxide, to allow oxygen ions to migrate and generate a measurable voltage.
Right.
But the vaporized sulfur compounds in JP8 exhaust will physically bond with that zirconium dioxide matrix. It effectively poisons the catalyst, blinding the sensor to the oxygen levels in the exhaust stream.
It essentially suffocates the very instrument designed to measure the breath of the engine.
That's exactly what happens. To counteract this, the specifications mandate highly specialized protective coatings on the sensing elements. They often utilize advanced nanomaterials that physically repel sulfur molecules while remaining porous enough for oxygen ions to pass through.
That's incredible.
It ensures the engine control unit always receives highly accurate telemetry to balance the combustion equation. That prevents the engine from running too rich and fouling the spark plugs, or too lean and melting the rotor housing.
And there's also the stealth aspect of the exhaust, right?
Oh, absolutely. The exhaust manifolds themselves must be treated with low infrared signature thermal barrier coatings.
Because heat is basically a giant target.
Exactly. In a contested combat environment, an exposed, glowing red turbocharger manifold is a beacon for infrared-guided surface-to-air missiles. The conformal exhaust design tucks the plumbing tightly against the airframe, masking the thermal signature and significantly enhancing the survivability of the platform.
So we have established how the mechanical systems manipulate the raw physics of combustion, pressure, and chemistry. But regulating those chaotic physical forces requires a processing architecture that assumes failure is inevitable. Let's move into the paranoid digital brain governing this machinery. The document outlines the architecture for the FADEC, requiring a dual-channel ECU configuration lane A and lane B. But the true masterpiece of redundancy here, I think, is the requirement for a lockstep microcontroller unit.
Yeah, the lockstep architecture is the defining feature of high-integrity aerospace computing.
Okay, so how is it different from the processor in, say, my laptop?
In a standard multi-core processor, like the one in your laptop, the cores share the workload to process data faster. One core handles the web browser, another handles background tasks.
Right, they divide and conquer.
Exactly. But in a lockstep processor, you have two physical processor cores executing the exact same stream of instructions, clock cycle by clock cycle, completely independently.
Oh, so they're essentially doing the exact same math homework at the exact same time, completely isolated from each other.
Yes. And there is a separate hardware comparator circuit that monitors the output of both cores at the bus level.
Why go through all that trouble?
Because of where these things fly. At 30,000 feet, the atmosphere offers significantly less shielding against cosmic radiation.
Wait, cosmic radiation? Like from space?
Literally from space. High-energy neutrons can strike the silicon die of the microcontroller, physically altering the charge of a microscopic transistor.
You're kidding.
I'm not. This induces what's called a single event upset. It literally flips a binary 0 to a 1 in the processor's cache.
And if that flipped bit alters a critical calculation regarding fuel injector duration, the engine floods and dies.
But the comparator circuit catches it instantly. Because only one core was struck by the cosmic ray, the two cores will attempt to output different results on the very next clock cycle. The comparator detects the mismatch in a fraction of a microsecond.
And it cannot simply pop up a blue screen of death and ask the pilot to reboot the system.
No, the arbitration has to be violent and immediate. The architecture specifies a cross-channel data link and an independent hardware watchdog circuit. When that lockstep mismatch occurs in lane A, or if lane A's software hangs in an infinite loop, the watchdog detects the loss of a regular heartbeat signal.
And then what?
It instantly strips Lane A of its authority over the fuel and ignition drivers and transfers complete control to Lane B.
Just like that.
Just like that. The cross-channel data link ensures that Lane B was constantly being updated with Lane A's exact sensor telemetry and engine state just prior to the fault. The failover arbitration happens so rapidly that the physical engine hardware, the spark plugs, and the fuel injectors, they never miss a single combustion event.
So the drone experiences a catastrophic computing failure, isolates it, and continues flying without a single drop in engine RPM.
Pointing out to the listener, it's like having a pair of co-pilots sitting next to each other, constantly checking each other's math every microsecond. If one gets it wrong, the other immediately takes the yoke.
That is wild. But the system is designed to survive computing faults, sure, but it also has to survive a total blackout. The document requires a 100 millisecond airborne hot restart capability.
Yeah, this is intense.
So if the primary power bus suffers a massive transient spike and everything shuts down, the engine loses spark and basically begins to windmill in the slipstream.
Right. A windmilling engine is generating no thrust, but the internal components are still spinning due to the airflow over the propeller.
Okay.
Within 1/10 of a second of power being restored, the FADEC must reboot its real-time operating system.
In 1/10 of a second.
Yes. It must initialize the sensor bus, read the crank position sensor to determine exactly where the rotor is in its spin cycle, calculate engine speed, access the volumetric efficiency tables, calculate the required injection pulse, and fire the ignition coil to catch the engine before the aerodynamic drag slows it down past the point of recovery.
That is just. Booting an operating system and executing complex combustion algorithms in 100 milliseconds. That requires incredibly optimized bare metal C code without an ounce of software bloat.
It really is the digital equivalent of catching a falling knife in the dark.
And that logic extends to communication failures too. If the FADET loses its data link with the primary flight computer, meaning it no longer receives throttle commands, it executes a comm loss failsafe. It overrides the last known command and locks the throttle to a predetermined safe loiter setting, which they say is typically around 40% power.
The logic there is based on predictable flight profiles. If the engine shuts down, obviously the aircraft is lost, but if it locks at maximum continuous power, it will quickly exhaust its fuel supply, or it might exceed its structural speed limits and literally tear itself apart.
Neither is good, so why 40%?
A 40% throttle setting provides just enough thrust to maintain altitude in a stable holding pattern. The engine management system essentially isolates itself and keeps the aircraft airborne, buying critical time.
Item 4, what?
For the automated flight computer to initiate a return-to-base protocol using GPS waypoints, or for the ground control station to reacquire the encrypted data link.
Okay, so the FADE is incredibly paranoid about external failures,
Yeah.
but it is equally paranoid about the sensors physically wired to it.
It doesn't trust anything.
Right. We discussed the manifold absolute pressure, or MAP, sensor earlier, which is critical for determining the density of the air entering the engine. The document outlines this highly specific sensor degradation strategy. It states that if the MAP sensor fails, the system must immediately fall back to an alpha N algorithm. This is where basically software math steps in to save broken hardware.
Exactly. In a nominal state, the system uses the MAP sensor to directly measure the pressure inside the intake manifold. It combines that data with the intake air temperature to calculate the exact mass of the oxygen entering the cylinder. That strategy is known as speed density.
Okay.
Sensors mounted to a vibrating superheated Wankel engine. They will eventually fail. It's inevitable. The wiring harness might chafe, or the internal sensor diaphragm might rupture.
Wait, let's look at the sensor degradation strategy. If the drone goes blind and loses a critical pressure sensor like that, how does the engine not just quit immediately? If the MAP sensor flatlines or starts transmitting garbage data, relying on it would cause the ECU to inject wildly incorrect fuel volumes, stalling the engine instantly, right?
It would. But the software identifies the out-of-bound sensor data and immediately ignores it. It switches to those alpha N lookup tables.
What does alpha N mean?
Alpha represents the precise angle of the throttle position sensor, literally how far the physical butterfly valve is open. N represents the engine RPM.
Oh, I see.
See, long before the software was ever loaded onto the drone, engineers ran the specific engine model on a laboratory dynamometer for hundreds of hours. They manually mapped the engine's volumetric efficiency at every possible combination of throttle angle and RPM. They mapped the entire physical breathing capability of the engine in a lab. So if the throttle is open exactly 35% and the engine is spinning at exactly 5,000 RPM, The engineers know with high statistical certainty exactly how much air the engine is inhaling, even without a pressure sensor to confirm it.
Precisely. The Alphen algorithm abandons direct measurement and relies entirely on this mathematically proven, hard-coded reference table.
It's basically the brain doing a backup math problem.
Yeah. It's less adaptable to sudden altitude or temperature changes than the speed density method, but it guarantees the engine receives a combustible fuel mixture. It keeps the fire lit. The entire degradation strategy is built on the premise that the hardware will lie to you, and you must have an empirical mathematical model ready to take over. It's an engineering philosophy of paranoia. Everything will break. And managing all these microsecond decisions requires a data network capable of supporting that speed without bottlenecking. The specifications mandate the use of deterministic communication networks. They list CAN Aerospace, UAV CAN, and MIL-STD-1553B, operating at data transfer rates up to 1 megabit per second.
Now, for a desktop computer, 1 megabit per second sounds incredibly slow.
Yeah, you couldn't even stream a YouTube video on that.
Right. But in avionics, we aren't streaming high-definition video. We are transmitting tiny packets of vital telemetry exhaust, gas temperatures, bus voltages, fuel pressures. The key requirement here is that the network must be deterministic.
Okay, what does deterministic mean in this context?
Determinism is the fundamental difference between commercial networking and avionics networking. Standard Ethernet or Wi-Fi operates on a probabilistic model, specifically carrier sense, multiple access with collision detection.
That's a mouthful.
Basically, when a device wants to transmit data, it checks if the line is clear. If two devices transmit simultaneously, the data packets collide. The network detects the collision, and both devices wait a random number of milliseconds before trying again.
Which works perfectly fine if you are loading a web page and the router takes an extra 4 milliseconds to resolve a collision.
Right, you don't even notice. But in an unstable aerodynamic platform flying at 200 knots, a 4 millisecond delay in a control surface command or throttle adjustment, that can induce an unrecoverable aerodynamic oscillation.
The drone flips over.
Exactly. The network cannot afford collisions. MIL-STD-1553B, which was originally developed for the F-16 fighter program, physically prevents collisions through a strict command and response architecture. A central bus controller dictates exactly when every single node on the network is allowed to speak.
It is a highly regimented, time-triggered protocol.
Yes. When the FADE needs to broadcast the engine RPM to the primary flight computer, it does not compete for bandwidth. The architecture guarantees that the data packet will arrive at its destination within a mathematically guaranteed time frame every single time, without exception.
It's amazing.
Furthermore, MIL-STD-1550B uses differential signaling over fielded twisted pair cables with transformer coupling. Meaning it's incredibly resilient to the massive electromagnetic interference present in a military aviation environment.
Which provides a perfect bridge to the electrical power generation and the sheer environmental violence this system must survive. Because none of that deterministic networking or lockstep processing matters if the electrical lifeblood of the drone is compromised. We're digging into the power architecture and the MIL-SPEC environmental tolerances now. The document requires dual permanent magnet alternators, or PMAs, generating power at 28 volts direct current, complying with the MIL-STD-704 military aircraft power quality standard.
A permanent magnet alternator is highly reliable because it eliminates the need for slip rings or brushes, which, wear out and generate electrical noise over time.
Right.
But the alternators are finite resources, and the electrical demands of a modern UAV are highly variable. You have the baseline draw of the FADEC, the fuel pumps, and the ignition coils, but you also have massive transient loads.
Like what?
The multispectral targeting gimbal, high-powered encrypted radio transmitters, electrically heated pitot tubes for anti-icing.
So the system requires a generator control unit capable of dynamic generation load shedding, which, from my understanding, is the electrical equivalent of triage.
Exact.
So load shedding is basically like when my house is running on a backup generator during a winter storm, and the smart panel automatically shuts off the microwave and the TV so the heater doesn't trip the system.
That's spot on. Now scale that analogy up to a flying aircraft. If the drone flies into freezing rain, the anti-icing systems automatically engage, drawing huge amounts of current. If the encrypted radio transmits a high bandwidth burst simultaneously, the total electrical demand can instantly exceed the capacity of the dual PMAs.
And when demand exceeds supply, the voltage on the 28-volt bus begins to sag.
Right. And the engine control computers have a strict minimum operating voltage. Furthermore, those 25 kilovolt ignition coils we talked about, they rely on that primary bus voltage to generate the spark plasma.
Oh, right. So if the bus voltage drops too low, the spark weakens, the heavy JP8 fuel fails to ignite, and the engine stalls.
Yes. So the generator control unit monitors the bus voltage in real time. Before the voltage sags to a critical threshold, it executes the load shedding algorithm. It communicates with the central flight computer to identify non-essential electrical loads.
It just kills them.
Mercilessly. It will cut power to the secondary heated payload bay, disable the backup telemetry radio, or power down the synthetic aperture radar. It amputates the peripheral systems to protect the core voltage, ensuring the spark plugs keep firing and the FADEC remains online.
And then when the storm passes?
Once the transient load passes, for example, the aircraft climbs above the icing layer and the heaters disengage, the GCU seamlessly restores power to the shed systems.
It is a ruthless prioritization of survival over mission capability. And survival is definitely the core theme of the environmental testing standards outlined in this section. The document mandates compliance with MIL-STD 810H and RTCA DO160G. These are not merely functional tests. I read through them, and they are highly engineered torture chambers designed to accelerate the physical degradation of the hardware.
It is sheer violence. Let's look at the shock testing. The document calls out MILA's STD 810H method 516.8. It specifically mandates that the internal electronics must survive a 40G 11 millisecond half-sign shock pulse.
Well, 40G shock.
Yeah.
So that means that for 11 milliseconds, every single microscopic component inside that engine management system suddenly exerts 40 times its normal mass on its mounting points.
Yes. This simulates the violent deceleration of catching an arresting wire on a carrier deck or the explosive acceleration of a pneumatic catapult launch.
For context for our listeners, a typical commercial printed circuit board is populated using surface mount technology. Components are soldered directly to little pads on the surface of the board. If you subject a standard commercial ball grid array, which is a high-density microchip with hundreds of tiny solder balls underneath it, to a 40G shock, what happens?
The microscopic solder joints just fracture. The chip will literally rip itself off the fiberglass substrate.
Just pop right off. Have you ever dropped your phone in a puddle and panicked? Think about the peace of mind knowing the electronics in this checklist are IP67, sealed and tested to withstand a 40-gram impact. How do they actually make it survive that?
Extensive mitigation strategies. High-mass components like electrolytic capacitors are manually secured to the board using specialized aerospace-grade epoxy potting compounds.
So they glue it down.
Strongly. And the critical processors are underfilled.
What's underfilling?
It's a process where a capillary action epoxy is injected underneath the chip to bond it directly to the circuit board, relieving the mechanical stress on the microscopic solder joints. Then the entire circuit board is mounted inside the aluminum chassis using highly tuned elastomeric vibration isolators.
Like shock absorbers.
Exactly. They dampen the sharp kinetic spike of the 40G impact, spreading the energy over a longer time domain to prevent structural failure.
And the physical impacts are just the baseline. The standard also requires method 518.2 for ocean salt fog, simulating decades of exposure to highly corrosive marine environments. But the most invasive requirement, in my opinion, is method 508.7 for mold and fungus intrusion.
Oh, the fungus test.
Wait, they actually spray mold on it.
They do. See, when UAVs are deployed to high-humidity tropical environments, condensation forms inside the electronic enclosures, and many of the standard plastics, wire insulations, and even the polyurethane conformal coatings used to waterproof circuit boards contain organic compounds.
Just food.
To microscopic fungi, those coatings are an all-you-can-eat buffet. If mold spores colonize the surface of a circuit board, they form a web of highly conductive mycelium. They trap moisture against the exposed pins of the microprocessors, creating parasitic electrical pathways that can short out the high-speed data buses.
That is disgusting, but also fascinating. So how do they test for it?
The testing is remarkably primitive, but incredibly effective. The electronics are placed in a highly controlled, warm, humid environmental chamber. They are physically sprayed with an aerosolized mixture of aggressive fungal spores, typically species known to rapidly consume organic polymers.
Wow.
The hardware is left in the chamber for 28 days. If any biological growth is detected on the circuit boards or the wire harnesses, the materials fail the certification.
So how do you beat the fungus?
The engineers are forced to specify biologically inert conformal coatings, like parylene. It's applied in a vacuum chamber as a vapor, creating an impenetrable microscopic polymer barrier that fungi simply cannot metabolize.
That's incredible. So the system has to survive fungus, shock, and salt. but it also has to survive the invisible warfare of the electromagnetic spectrum. The document requires defense against electromagnetic interference per mil STD-461G and high-altitude electromagnetic pulses EMP per DO-160G.
A modern combat theater is just saturated with high-energy electromagnetic radiation. You have naval radar systems sweeping the sky with megawatts of RF energy, active jamming pods attempting to blind communications, and the constant threat of lightning strikes or localized EMPs.
It's a hostile environment even if you can't see it.
Right. When a drone flies through the beam of a high-powered radar, the electromagnetic energy interacts with the copper wiring harness of the engine management system. The wires act as unintended antennas, converting the RF energy into stray electrical currents.
And if those induced currents travel down the wiring harness and reach the sensitive input pins of the FADT, I'm guessing bad things happen.
Very bad things. The lockstep microprocessors might interpret that random noise as a legitimate command to advance the ignition timing or open a fuel injector at the absolute wrong moment in the combustion cycle.
Boom.
Exactly. So to mitigate this, the architecture demands a comprehensive Faraday cage design. The external aluminum housing of the FADT is heavily shielded, with conductive gaskets sealing every seam.
Like the fortress.
And the external wiring harnesses are wrapped in braided metal shielding that terminates directly to the chassis ground. It intercepts the RF energy and shunts it harmlessly into the airframe before it can ever penetrate the internal circuitry.
And for catastrophic transient spikes, like a direct lightning strike.
The system utilizes transient voltage suppression arrays. A lightning strike injects tens of thousands of amps into the airframe in microseconds. The input power lines of the FADT are equipped with specialized avalanche diodes.
Avalanche diodes.
Yeah, under normal 28-volt operation, these diodes are completely invisible to the circuit. But the millisecond a massive voltage spike hits the line, the diodes break down and become highly conductive. They instantly shunt the destructive energy directly to ground, sacrificing themselves to protect the delicate silicon processors downstream.
Which brings us to the actual foundation of the physical hardware, the manufacturing standard of the circuit boards themselves. The document mandates IPC 6012DS Class 3, specifically noting defense and aerospace grade. Now, for context, the commercial electronics in, say, a smartphone are built to Class 1 or Class 2 standards. Those prioritize manufacturing speed and acceptable failure rates over absolute perfection.
Right. If a copper trace inside a commercial circuit board is slightly misaligned, or if the microscopic plating inside a via, which is the hole that connects the different layers of the board, is slightly thin, the phone will likely still function for a few years before thermal fatigue breaks the connection.
And you just buy a new phone.
Exactly, but in IPC Class 3 manufacturing, there is no acceptable failure rate. The physical tolerances are microscopically tight.
How tight are we talking?
Well, the annular rings, the copper pads surrounding those vias, they must be perfectly concentric to ensure maximum structural integrity during thermal cycling. Every single solder joint on the board must exhibit a perfect metallurgical bond. It must form a specific, mathematically defined concave curve called a fillet that guarantees maximum mechanical strength against that high-frequency Wangle engine vibration.
And how do they know they achieve that?
During manufacturing, the circuit boards are subjected to automated optical inspection, and critical areas are literally X-rayed in 3D to ensure there are no microscopic air voids hidden inside the soldered joints underneath the microchips.
X-raying the solder.
It is a philosophy of zero-defect manufacturing, because a cracked solder joint at 20,000 feet means the loss of the aircraft.
Okay, we've spent this entire session exploring the physical and digital armor engineered into this system. We've covered the lockstep microcontrollers, the heavily shielded Faraday cages, the pressurized fuel lines fighting vapor lock, and the X-rayed IPC Class 3 solder joints. The engineering team has built an absolute fortress of a machine.
They have.
But the final section of our document, Section 8, Deliverables, demands something that feels almost contradictory to me. After proving the hardware can survive 40G shocks, fungus chambers, and lightning strikes, the regulatory authorities demand hundreds of pages of theoretical mathematics. We are talking about functional hazard assessments, fault tree analysis, and failure mode and effects analysis, the FMEA. We just talked about blasting this engine with sand, lightning, and 40-degree shocks. After all that physical proof, why do we need hundreds of pages of fault trees and traceability matrices? Doesn't the physical test prove it works?
I get that a lot. If we connect this to the bigger picture, empirical physical testing only provides a snapshot of reliability. Exposing a prototype to a 40G shock and verifying that it still functions proves that the architecture can survive that specific event exactly once under controlled laboratory conditions.
Oh, I see.
But aviation safety regulators are not interested in what happens on day one. They are interested in what happens at flight hour 5000, after the system has been subjected to years of thermal cycling, micro vibrations, and material fatigue.
And you can't test for that physically.
Right. You cannot physically run a test engine in a chamber for 50,000 hours to prove its long-term reliability before putting it into production. It would take years. The mathematical deliverables, the FMEA, and the fault tree analysis, they bridge the gap between empirical testing and long-term statistical probability.
Let's break down the mechanics of the failure mode and effects analysis, because I read through the process, and it is an incredibly tedious bottom-up approach to engineering.
Extremely tedious.
The reliability engineers take this schematic for that IPC Class 3 circuit board, and they look at every single individual component, every resistor, every ceramic capacitor, every field effect transistor. And for each microscopic part, they ask a series of specific questions, like how can the specific component fail? Can it short circuit? Can it fail open? Can its resistance value drift out of tolerance due to heat?
And they don't just guess those answers. They utilize massive military databases of component reliability that track the historical failure rates of that specific type of resistor over millions of hours of operational use.
Wow.
Once they determine how it can fail, they have to determine the effect of that microscopic failure on the overall system. If capacitor C104 shorts to ground, does it merely cause a slight fluctuation in the analog to digital converter reading the engine temperature? Or does it completely crash the primary 5-volt power bus and shut down the lockstep microcontroller?
And if the analysis reveals that a single capacitor failure leads to a catastrophic system shutdown,
that is a single point of failure. The architecture is immediately rejected, and the hardware engineers must redesign the circuit to include redundancy, perhaps by placing 2 capacitors in series so that if one shorts, the circuit remains protected.
it's just layer upon layer of safety. And conversely, the fault tree analysis, the FTA, takes a top-down approach, right?
Yes. The engineers start with the ultimate catastrophic event, for example, total loss of engine thrust. They then map out every single logical pathway that could lead to that event. Did the fuel pump fail? Did the lockstep processor halt? Did the engine ingest a bird?
And then what?
They assign statistical probabilities to each branch of the tree, utilizing viable distributions to model the wear-out phases of the mechanical components.
So by combining the bottom-up data from the FMEA with the top-down logic of the fault tree analysis, the engineering team can calculate the system's overall MTBF, the mean time between failures.
Exactly. This is the mathematical proof the regulators demand. It demonstrates, with a high degree of statistical confidence, that a catastrophic failure resulting in the loss of the aircraft will only occur, for instance, once every 100,000 flight hours. The aviation industry regulates based on mathematical probability, and these documents are the ultimate receipts.
And all of this theoretical modeling and software traceability culminates in the flight test plans, right?
The final stage. Bolting this heavily documented, violently tested, mathematically proven engine management system to the actual airframe and flying the specific profiles defined by the means of compliance.
And I'm guessing the flight telemetry is analyzed to ensure the real-world performance perfectly mirrors the theoretical models.
Spot on. Only when the empirical flight data aligns perfectly with the fault trees and the DO-178C traceability matrices does the regulatory authority finally sign off on the architecture.
It's exhausting just talking about it. When we started this analysis, we were looking at a highly dense, translated customer requirement document, a simple checklist for a UAV engine management system. But unpacking the logic behind these requirements has exposed an absolute masterpiece of systems engineering.
It really is.
We have analyzed the brutal thermodynamics of atomizing heavy JP8 logistics fuel in a Wankel rotary engine at -30 degrees Celsius using 25 kilovolt plasma ignition. We have examined the elegant physics of dynamic pressure regulators continuously flushing fuel lines to prevent high-altitude vapor lock.
We have dissected the staggering paranoia of the digital architecture, the lockstep microcontrollers performing microsecond hardware arbitration to survive cosmic ray strikes.
Right.
And those alpha-N volumetric efficiency tables ready to execute backup math the millisecond, a manifold pressure sensor degrades in flight.
We have explored the brute force survival tactics of smart load shedding, the zero-defect IPC Class 3 soldering required to withstand 40G kinetic shocks, and the extensive Faraday shielding designed to repel electromagnetic warfare. And finally, the uncompromising statistical mathematics of fault trees and DO-178C that prove the entire integrated system is safe to share the sky with commercial aircraft.
It forces a complete recalibration of how you view these platforms. The sheer volume of human ingenuity, physics manipulation, and hardware paranoia concentrated into that small aluminum box is, frankly, one of the great quiet triumphs of the modern aerospace industry.
It is an incredible technological achievement. But as we close this deep dive, I want to leave you with a final engineering puzzle to consider. We've spent this entire session exploring how dense, heavy, and redundant this architecture must be to survive the rules of the sky. We need dual permanent magnet alternators, pressurized return lines, twin lockstep processor cores, and heavy aluminum Faraday cages.
It all adds up to a lot of weight.
Exactly. But the relentless trajectory of drone technology is pushing towards smaller, highly capable micro-UAVs platforms, the size of a bird, that still need to operate in these same hostile military environments and adhere to these exact same aviation safety standards. So how will the next generation of engineers manage to shrink this massive web of redundancy into a package that fits in the palm of your hand, without violating the fundamental laws of thermodynamics or sacrificing the uncompromising DO-178C safety matrix we just unpacked?
That is a big question.
It is the next great frontier of engineering paranoia, and the solutions will undoubtedly redefine the limits of material science and microprocessing. Thank you for joining us on this extensive deep dive into the architecture of modern aviation. Keep questioning the mechanics behind the technology, and we will see you next time.